Picture a device so tiny it could rest comfortably in the palm of your hand, yet so powerful that it challenges everything we think we know about computation. This isn't a futuristic fantasy or a science fiction concept. It's a real technological achievement that has forced scientists to ask questions they never expected to face. Near the end of 2024, Google introduced a quantum processor called *Willow. During one of its benchmark demonstrations, the chip completed a highly specialized calculation in only a few minutes. According to Google's comparison, a traditional supercomputer would require an unimaginably long period, far beyond the lifetime of the universe, to perform the same benchmark. Whether or not that comparison applies to practical problems, the result immediately captured the attention of researchers around the world. The most fascinating part wasn't simply how quickly the calculation finished. It was what the demonstration suggested about the nature of quantum computation itself. The scale of the mathematical problem seemed so enormous that it challenged our intuition about how information can be processed. To appreciate why this matters, it helps to understand how ordinary computers work. Every phone, laptop, and supercomputer stores information using bits. Each bit has only one value at any given moment, either 0 or 1. Even the fastest machines still process information through enormous numbers of logical operations carried out step by step. Quantum computers operate according to a very different set of rules. Instead of ordinary bits, they rely on quantum bits, known as qubits. Unlike classical bits, qubits can exist in combinations of multiple quantum states until they are measured. This property, called superposition, allows quantum systems to represent information in ways that have no direct equivalent in classical computing. The real advantage appears when multiple qubits become connected through a phenomenon called entanglement. Once entangled, the behavior of one qubit is linked to the others in ways that classical physics cannot easily explain. As additional qubits are added, the complexity of the overall quantum system grows extraordinarily fast. With a processor containing more than 100 high-quality qubits, the number of possible quantum configurations becomes staggeringly large. The figures quickly exceed numbers that humans can meaningfully imagine. This doesn't mean the computer stores every possible answer inside its hardware, but it does highlight how dramatically quantum information differs from classical information. That distinction has inspired one of the biggest questions in modern physics. When a quantum processor performs an incredibly complex calculation, where is that computation actually taking place? Unlike a classical computer, which follows a clear sequence of operations inside its physical circuits, quantum systems evolve according to the mathematical rules of quantum mechanics. Their behavior cannot always be visualized using familiar ideas about objects moving from one place to another. For decades, physicists have proposed different interpretations to explain what quantum mechanics really means. One of the most discussed is the many worlds interpretation. According to this idea, every quantum event could correspond to multiple possible outcomes that exist in separate branches of reality. It remains an interpretation, not an experimentally proven fact, but it has fascinated both scientists and philosophers for generations. Some researchers have even suggested that this interpretation offers an intuitive way to think about quantum computation. Rather than imagining a quantum computer trying every solution one after another, they describe it as evolving through an enormous mathematical landscape that has no classical counterpart. It is important to understand that this idea remains highly debated. There is currently no scientific evidence proving that quantum computers literally communicate with parallel universes or borrow computing power from other realities. Nevertheless, the extraordinary behavior of quantum systems continues to inspire discussions about the deepest structure of nature itself. This is one reason the Willow processor attracted so much attention. Beyond the impressive benchmark numbers, it reminded the scientific community that quantum mechanics still contains mysteries we do not fully understand. Every advance in quantum technology pushes us to rethink assumptions that once seemed unquestionable. Rather than providing final answers, Willow has reopened some of the biggest questions in science. What exactly happens inside a quantum computation? Why does nature allow information to behave in such unusual ways? One of the most remarkable aspects of quantum computing is that it doesn't simply examine possibilities. It allows those possibilities to influence one another through a phenomenon known as quantum interference. Instead of checking every answer individually, the quantum system evolves so that incorrect outcomes gradually lose significance while the correct ones become more likely to appear when the computation is measured. This process is one of the reasons quantum algorithms can outperform classical methods for certain specialized tasks. Yet despite decades of research, the deeper meaning behind quantum interference remains a subject of scientific debate. Different interpretations of quantum mechanics describe it in different ways, and none has been universally accepted as the final explanation. Among these interpretations, the many worlds idea often attracts the most attention. It suggests that quantum events may correspond to multiple branches of reality that evolve independently before their mathematical descriptions produce the probabilities we observe. While this concept is fascinating, it remains speculative and has not been experimentally confirmed. Because of this, scientists are careful not to claim that quantum computers are literally communicating with alternate universes. Instead, they focus on the mathematics, which successfully predicts experimental results regardless of which interpretation someone prefers. In other words, the calculations work, even if the philosophical explanation remains uncertain. Beyond these theoretical questions, Willow demonstrated something that may have even greater practical importance. For years, one of the biggest obstacles in quantum computing has been error correction. Quantum systems are incredibly delicate. Tiny changes in temperature, microscopic vibrations, or stray electromagnetic signals can disturb fragile quantum states. When that happens, valuable information is lost before the computation can finish. This challenge, known as decoherence, has limited the development of large-scale quantum machines for decades. Traditionally, increasing the number of qubits also increased the likelihood of errors. Building larger quantum processors often meant creating systems that were more difficult to control and less reliable overall. Engineers constantly faced a trade-off between expanding computational power and maintaining stability. Willow offered encouraging evidence that this trend can be improved. Google's researchers reported that as they refined the processor and expanded its error correction techniques, the logical error rate decreased instead of increasing. While significant engineering challenges still remain, this result suggests that scalable quantum computing may be becoming more realistic than many experts previously believed. If future generations continue this progress, the impact could extend across countless scientific fields. Chemists may simulate complex molecules with unprecedented precision, accelerating the discovery of new medicines. Material scientists could design entirely new substances with extraordinary electrical or mechanical properties. Researchers studying energy, climate, and advanced manufacturing might solve problems that are currently beyond the reach of even the world's fastest supercomputers. Artificial intelligence could also benefit from advances in quantum technologies. Although quantum computing is not expected to replace conventional AI systems, future hybrid approaches may eventually help solve certain optimization and simulation problems much more efficiently than classical hardware alone. Yet every major technological leap raises new questions alongside new opportunities. History shows that transformative inventions often arrive before society fully understands their long-term consequences. Electricity, nuclear physics, and the internet each reshaped civilization in ways few people initially predicted. quantum technology may represent another turning point of similar magnitude. Unlike classical machines that rely on certainty and clearly defined logic, quantum computers operate by exploiting probabilities encoded within the laws of quantum mechanics. Instead of avoiding uncertainty, they use it as a computational resource. That idea alone challenges centuries of intuition about how information should behave. Whether future discoveries ultimately confirm or reject interpretations like many worlds, Willow has already accomplished something significant. It has demonstrated that quantum engineering is rapidly moving from laboratory experiments toward practical technology. As researchers continue improving these systems, they may unlock capabilities that seem almost unimaginable today. The story of quantum computing is therefore about far more than building faster processors. It is about exploring one of the deepest scientific frontiers ever investigated. Every new breakthrough teaches us a little more about the hidden mathematical structure governing the universe and reminds us that our current understanding of reality may still be only the beginning.